This interim presentation for ME452 will be on the foldable scooter. The foldable scooter is a compact personal transportation device that's easy to store and transport and has a foldable frame to allow it to get into a smaller size. It's convenient for commuting short distances and has adjustable handlebars for steering and different user heights. It's also got a platform to stand on, 2 to 4 wheels for movement, and there's different versions available, including electric.
In terms of production volume, we've estimated the US demand to be about 5 million scooters per year, with the global market size valued at about $70 billion as of 2022. You can see in this graph to the right that the market shows an increasing popularity for electric scooters, and Razor, one of the most popular scooter brands, has sold over 50 million scooters in the last 25 years.
The primary customers for scooters are going to be children, teens, and young adults, or also commuters in urban areas. The secondary customers will be parents buying for their children, recreational users like people at skate parks, or schools and community centers.
In this slide, you can see an exploded view of the scooter from SolidWorks on the right, and on the left, you'll find a list of parts that go into making the scooter.
This is our FAST diagram. It describes the functions that the scooter is able to perform. Our main function branch relates to controlling the mobility of the scooter in favor of the rider.
In assembly sequence 1, we begin with the base assembly. Then the rear wheel assembly is added with brake and wheels. The handle lower assembly is then attached, followed by the front wheel assembly with wheels. Next, the handle upper assembly is inserted and fastened. All fasteners and standard parts are assembled and torqued as required in the process. For assembly sequence 2, we begin with the base assembly in place. Attach the handle lower assembly in the front. Then add the front wheel assembly with just inner shaft and handle plate inserted in handle lower assembly. Next, the handle upper assembly is inserted. Finally, the rear wheel assembly is attached and wheels are torqued with all the fasteners on.
When comparing the two sequences, we found that sequence 1 is more advantageous. The two sequences are similar in many aspects, and although sequence 2 is better for testing sub-assemblies, due to the early addition of the front wheel assembly, the early addition of the handlebars makes it more awkward to transfer and handle, leading sequence 1 to be much better on that front. The function component mapping matrix maps the components to the functions detailed in the FAST diagrams. Most components only serve one or two functions, and the most popular functions are changing direction and supporting the rider, both which have 6 components involved. These could be the basis of a redesign for more efficient assembly and manufacturing.
Here's our bill of materials. Considering assembly sequence 1, the assembly time and cost was estimated as per standards. We have assumed that the assembly is done manually. The total cost is estimated to be $53, which is 50 to 60% of the retail price of a similar product. Most of the parts are manufactured by sheet metal forming, and the rest are procured as standard parts.
Here, we classified parts based on their manufacturing and assembly cost and their functional importance. This is meant to help us consider elimination or to let us know if we need to keep some parts as they are.
This is our functional differentiation table, where we separated our product functions into those that are common for both our primary and secondary customers and those that are different. Both groups of customers care about the convenience and dependability functions of the scooter, while the functions that govern the way the vehicle is ridden vary for each customer group. The component commonality table is derived from the functional differentiation table, as well as the function component mapping matrix. The big thing to note here is that all parts can be simplified to 5 modules, including the base, upper and lower handle, and the front and rear wheel. The hinge was not considered a module, as the spring is the only platform integral to its use.
Here, we have two variants of the foldable scooter, which are targeted at the primary and secondary customers respectively. For the primary customer of children and commuters, we have a basic wheel design which allows for use on standard surfaces like sidewalks. For the secondary customer of recreational users, we have a rugged wheel variant which provides more grip for the more unusual surfaces.
Finding a common interface is an integral part of design for manufacturing and assembly. Doing this allows a large amount of time and hence money to be saved during the process. When looking specifically at our foldable scooter, we see that 6 different screws and nuts are being used as part of the product. To combat this issue, we will look to simplify all fasteners and nuts down to one common screw and nut, therefore representing one common interface.
Here, in the original product family assembly diagram, we see that product differentiation happens at an early stage when the wheels are installed early in the assembly process. Additionally, it can be noted that in this sequence, each part is painted before it is secured to the assembly. This generates several extra steps in the assembly process and creates repetition among several steps that occur in both variants. In the revised product assembly diagram, we use delayed product differentiation to optimize the assembly process. In this process, we saved the attachment of the wheels for the last step as this part differs between the two variants. Until the final step, we have a generic subassembly which can accommodate either the basic wheel design or the rugged wheel design. Additionally, waiting to paint the scooter until the final step deletes painting the parts in between each assembly step.